I
All
can
right.
see the you can see the sign.
All right, thanks. So today well, we'll see how it goes. But I wish we could finish the whole slides. We have to focus on the added part, but the other parts like the subtractor and the multiplier, it's not that hard. We're just gonna go fast on that. But yeah, I repeat a little bit about last week lesson. The delay of the ripple carry adder and how we improve that using the carry look ahead adder and how we improve the carry look ahead adder. Okay. All right. Guys ready? Everyone honestly had your breakfast, but it's Ramadan and most of you are fasting, I guess. So hopefully you're not fall asleep during the class because it is a very important chapter, right? Okay. Let's recall what we did in the last class. So in the last class, we learned about the delay in the ripple carry adder. Okay, to find the delay, you have to find the critical. Wow, that's thick. Okay. Okay, to find the delay, we have to find the critical path delay. Okay, which is the longest path, longest and having the highest delay. Okay, which is for n-bit ripple carry adder is this one. In this figure here, this example figure here is a 4-bit ripple carry adder. And we divide it into 3 stages, which is called the stage 0 here on the stage 0 on the first full adder. So we have 4 full adder here. It's not, the block is not seen. It's not drawn here, but remember we have 4 full adder. So the first stage is on the first full adder, and the second stage is the intermediate stage. In the intermediate full adder. And then the last full adder will be the stage n-1. So in the stage 0 here, the stage 0, we will see the delay is 4 tau because it's from A in here until C1. So it's A0 until C1. Well, you could choose B0 also, but let's just choose one, which is A0. Going through an XOR, that's 2 tau. And then going to an N, that's another tau. And going into an OR, which is another tau. So it's tau. And then in the second stage, another color, is the intermediate stage, okay, which is continuing from the where we last on the first stage, going into an end, which is the tau. Hopefully you can see what here. Going into a tau. then another OR, another AND, and another OR here. So it's from C1 to C3 total, and then the last stage is on the last flip-flop, and not flip-flop, sorry, last full adder. Okay, here from C3 going into an XOR. So it's A to S3. So for a 4-bit ripple carry adder, the delay is 10 tau. 10 tau. And in general, can calculate the propagation delay of a n-bit ripple carry adder using this formula. Remember? Okay, so how can we improve this? How can we improve this? We've done this last week. Okay, we're gonna improve this using a ripple carry carry look ahead adder. Okay, where in carry look ahead adder, we're gonna solve carry that is unknown at stage 0. Right? So because in the ripple carry adder, the carry is propagate, right? The carry is propagate, is ripple to the next full adder like this. So we cannot not run the second full adder here before we got the inputs carry from the previous full adder. Okay. So there's a wait there, and we don't want that wait. So instead of waiting, we want to solve the carry. Okay. The input that we need is C1, C2, and C3. And of course, we can also calculate C4, but we don't really need to calculate C4 during the stage 0, because that will be like the end answer, the end solution for the 4-bit ripple carry adder. So instead of waiting for the carry in, calculate C1, and C3. So how we're going to calculate that? We're going to use the carry that we know from the start, which is the C0. And we have seen this last week. So we can expand the equation, each of the equations, C1, C2, C3, C4, by replacing the C2 in C1 with this value. So we can only have the equation with only G, P, and C0. Okay, at the end, we only have G, P, and C0. This is known as the first stage. Okay, it's stage 0. G is known as the first stage because G is AI, EI, and E is AI plus E. Okay, So if this is good, then what is the delay, right? So before that, we can realize, we can realize the calculation of C1, C2, C3, C4 into a circuit that looks like this. Okay, remember that I always remind you that keep the equation, okay, keep it in SOP, sum of product, so that we will only have two levels, okay, like this, level 1, level 2. And it's a two level of AND and OR. So this will be the total for this circuit. Okay, the whole circuit is 2 tau. Because the calculation is parallel on the same time. Parallel at the same time. So it's 2 tau. Right? So our 4-bit carry loop ahead adder, which must be better than the 4-bit ripple carry adder, the total delay is 5 tau. Okay. Okay, so the longest path or the CPD is from A, G, and then from A0 to G0, and then from G0 to C3, and then from C3 S3. Right? So this is from A0 to G0. Okay, we only need tau. From G0 to C3. Okay, this is inside the carry load ahead generator here is this circuit. Okay, the circuit that calculates the carry. So it's 2 tau. And this is another 2 tau. Okay. Why? Because inside the PFA is this circuit. Okay, remember this circuit. Okay. So let's see the inside. Snipping tool here. That, copy that. Here. Right. And that. Then inside the PFA here. Inside, oops. Is okay. This is the PFA. So I just copy this and put it here. And another one of that here. So let's show you. Okay. So where is this T coming from, right? So here we have A, B, C carry, and then the T, the P, and the S. Okay. Can you see the writing? Too small? Problem?
Can.
Okay, can I? Okay, thanks. All right. So the tau, sorry, I keep saying T. So the tau here is coming from it's A to G. A to G. Okay, so it's going through one end, so that's why we got it found. Okay, and this one, carry look ahead generator here. Okay. This one, yellow, no yellow here. Red. So this one is from G0 to C3. G0 to G0 to C3. Going through an AND and an OR. So it's 2 tau. Then this one is C3 to S3. So this is C3 here and into S3. So there is one XOR. So it's 2 tau. Right? I hope it's clear. Okay. Why the carry loop head adder is having 5 tau in total. Okay. Carry loop head adder, okay, 4-bit carry loop header loop ahead adder has the delay of 5 tau. Okay, 5 tau. Right? We've done that last week, and then we knew that this is not the best solution because why? One, oh, green. One, we are adding more gates. Okay. Adding more gates means it is going to be a large hardware implementation. So that's not good. So carry look ahead adder is not the best solution for a high-speed adder, even though it has delay less than the ripple carry adder, right? The second problem is we know that the longer bit we put in this circuit, we're going to have fan-in problem. Fan-in problem. Because there's a limit on the number of wire coming into the gate, Okay? And we just want to put the limit as 4 or 5 wire here. So the maximum that want to go is 4-bit CLA, carry loop ahead adder. So if you want to have bigger bit size, like 12-bit adder using carry loop ahead adder, we just cascade the 4-bit carry loop ahead adder together. Okay, we cascade the 4-bit carry loop ahead adder together. Okay, right? But when we cascade that, okay, when we just simply cascade that, okay, the delay, okay, the longest path is coming in here, then going here, and then this block has to wait for the C4 to calculate, to compute, and generate C8. And then the next block here has to wait for the C8 calculate. Okay. And then to generate the S11, okay, the MSB of the answer. So the delay is here. Here is tau, and then one block is taking 2 tau, okay, for the 2 level, the SOP part, and then another 2 tau here, another 2 tau here, and the last one we have to go through 1 XOR, so it is 9, okay, 9 tau. And in general, we have this formula. In general, we have this formula, 9 tau. 9 tau, where M is the number of blocks. So we have 3 blocks here, 2 by 3 plus 3, that's 9. Right? So inside this is this. Inside the block. Okay. Maybe you can check later how we got the T and tau, 2 tau, and the last 2 tau here when we go through 1 XOR. Right? Okay. So for 4-bit, sorry, not 4-bit. It's more than 4-bit, right? So if you want to have 16-bit adder using the carry look ahead header cascaded like this, what is the delay? What's the delay? Muhammad Alif Ismat. What's the delay for 16-bit adder using the carry look ahead adder cascade like this? Muhammad Alif Ismat, are you sleeping?
Sorry, Sensei. He went to toilet.
He went to toilet. So you answer. Zamir Faik. You answer? Okay.
12.
12?
12 tau.
Okay, 12 tau. What's the calculation?
2 times 4.
2 times
3.
4
Plus 3.
plus 3. That's 12?
Tau.
Is this 12?
Time tau. Okay.
2 times 4 is?
Oh, my bad. It's 11.
11. Okay, 11.
It's 11 tau.
Okay. Right. In test, okay, I know. I also do this a lot of time. Okay, we make mistakes because we calculate in ahead and then we make mistake. Okay, 2 miscalculation. But this is not good if this is the test or final, right? Okay. Nothing can be done if you already write 12. Okay, so don't forget to recheck your answer. Okay, thank you, Zamir Faik. So, 16-bit adder using 4-bit carry look ahead adder block cascaded like this will have 11 tau. Okay, the propagation delay or the delay is 11 tau. All right. So, can we improve this? Yes, we can. Wait. What's the problem with this one? Okay. The problem is this block have to wait for this block to calculate C4 to begin its computation. And this block have to wait for this block to calculate C8, okay, to start its computation. So we have a waiting here and we don't want that. So it's the same thing as the ripple carry adder. That's what happened when you just cascade block, right? So what we want to do is to solve, okay, to solve the carry. So if we want to do 16-bit CLA, okay, carry load ahead adder. Okay. We're going to cascade 4 CLA, right? 4 4-bit CLA. Okay. We're going to cascade 4 of this block. But if we cascade it like this, problem is, okay, we have to wait for the carry to ripple. And what are the carry that ripple here? It's C4 because this is 4-bit inside this. C4, C8, C16, wrong, C12, 4-bit, 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 okay, and C16 here. Okay. So instead of waiting, you want to calculate. Just like the idea when we do the carry loop ahead adder. C0 here, we already know. But C4 here, C4, want to calculate. We have a circuit. Okay? C8. And C12. And also C16. Right? So the answer on how to improve it is to pre-calculate the carry. And we're going to pre-calculate the carry, okay, the same way as we did with the ripple carry adder to CLA process. Okay, where each block is a group. Okay, each block is a group. So the group generate is called the G0. Okay, make sure when we talk about the group, you're using uppercase. So to differentiate with this G, uppercase. Use uppercase G for the group generate. So the small g is just the generate, 1-bit punya generate, and the uppercase is the the group generate, and the uppercase P is the group propagate. So what is this and where is this coming from? Right? What is this and where is this coming from? So this is actually coming from C4. See, the G0 in P0 is inside the C4 interpretation here. So let's recall what is G4. I'm going to scroll up a little bit. So this is a C4. Okay, is bring it here. Okay, so this part is G0, C4. And then this part here is E0. Okay. So from C4, we group this part as the G0 and this part as the P0 so that we can have the equation back, which is the G0 plus P0 carry. Okay? And the carry that we want here is only carry 0, the carry that we know from stage 0, okay? We know from the beginning. Right? Hopefully that's not confusing. So the things that we want to calculate is C4, C8, C12, and C16. So we can calculate from C4, we can calculate C8. So C8 is G1 plus P1 plus C4. Okay, because this is where I got G0, right? So I got here you got G1. Okay. So G1, to calculate G1, you have to know what is C4. And we can replace this C4 with this. Only that, is this correct? I think this is a typo. This must be a typo. This is G1 plus P1, okay? Everyone, please correct this on your slide. So this is G0 here. And what? This is also a typo. This must be a G0. And yeah, that's it. Okay? So C4, which is a G0, P0, C0, is replaced like this. And C8 is here. Then this C12 is replacing this. Okay. So that we will end up with equation that only using G, P, and C0, which are the parameters that we know from the beginning at stage 0. Right? So this is how we group the carry look ahead adder. Now, we don't have to ripple or propagate this carry anymore because we have calculated here using the known parameter. Now, let's see how it affects the delay, right? Okay. So there are also 3 parts. So inside the CLA, inside the CLA prime here is the group is sorry because I keep scrolling, is this one, the 4-bit carry look ahead adder, right? 4-bit carry look ahead adder. So here we're going to the critical path delay. Critical path is from A0, G0, that is 3 tau, and then from G0 to C12, that is 2 tau. Because it's 2 tau because inside this is the SOP expression, right? It's this one. Okay. Same, just like the previously, we keep the equation as in the sum of product to maintain two level of circuit, so that the delay will be 2 tau. And this circuit realization is inside this box. So this box will have 2 tau as a delay. Right? And then the last part is from C12 to S15. That is 4 tau. Okay. Okay. It's very similar. Let's take this and bring it to the whiteboard. Okay, so this is a group carry look ahead adder. Group carry look ahead adder. And inside the CLA prime here, it's actually this circuit. The same circuit. And inside the PFA is this circuit. How to make this smaller? Alright, so why is this 3 tau? Why is this 3 tau? Because we are going from A0 to G0, and this is actually from here, okay, here, here until you got the C4, right? From here to here. So it's 3 tau, 2 tau. Okay. So this 3 tau is from this pass. So this is your G0, because this is a block. This is what it looks inside. From A0 to G0 is 3 tau, because you run from A0 and then to the carry look ahead generator here. So it's 3 tau, right? And then this one, you already understand. Why is it 2 tau? Because we have the 2 level. Okay. Okay. And then why is this 4 tau? Why is this 4 tau? Because it's from C C12. Right. So to screenshot them. This one. To retake this. Retake this. We want to know why is this 4 tau. So this is what it looks like inside this box here. Okay, so what's coming in here is C12. What's coming in here is C12. So this is C13, C14, and C15. Okay, so from C12, want to go to S3, S3, S15. S15. Okay, so we go through this path from C12. Okay, we go through the carry look ahead generator, then go up, go through the PFA, and go to the S15. Okay, so this is 2 tau. This is already 2 tau, and from here going into the PFA and to the S15, you are passing through an XOR, right? This one. You are going through an XOR from C to S here. So that is another 2 tau. So that's why we get 4 tau here. Okay. So total of the delay of group carry look ahead adder is 3 plus 2 plus 4. That is 9 tau. Okay. Which is better than the if we have to wait. Okay. It's just cascading without doing the grouping. Okay, so if we just cascade the block without doing any grouping, means we have to wait this block to generate C4 and then wait for this block to generate C8 and so on. Okay, the delay is 11 tau. Okay, but when we do the grouping, okay, the total delay is 9 tau. 9 tau. So there is an improvement. right? So that is all about the carry look ahead adder. Next, we're going to see another high-speed adder, which is a carry select adder. Okay. All right. So the example here is the figure here shows 8-bit carry select adder. This is 8-bit carry select adder, or you will always see the CSA. Okay. In the 8-bit carry select adder, the first 4-bit is here in this block. So this is bit 0 to bit 3. 0 to bit 3. And then here you will see bit 7, bit 4 to bit 7. Okay. So bit 4 to bit 7, we can select either to use this type of adder or this type of adder. So there are 3 4-bit adder inside the carry select adder that starts from here and end here and here. And the CPD is here. Okay. Right? So how this circuit works, okay? The 4-bit adder can be a ripple carry adder or a carry look ahead adder. So let's say we use the ripple carry adder. All these blocks are a 4-bit ripple carry adder, for example. It doesn't matter what is this because we're only concerned about this block for the delay. Because the critical path delay is going through this block, right? So we only care about this block. So this is a multiplexer. This is a multiplexer here. Okay. So first, the bit 0 until 3 is calculated, and we got the sum of bit 0 until bit 3. And then the carry of the 4-bit will go into a multiplexer. Okay. And then the multiplexer depends on the value of carry, which can be either 0 or 1. It can be either 0 or 1. It will choose which carry select adder to, which block of adder to use for the higher. If the carry 0, the carry will choose. If the carry and the C8 is rated to this. For is the total delay of the critical path is going to be this, and then plus is coming multiplex. Because if you recall the multiplexer using SOP, So that is 2 tau. And 4-bit adder depends on the type of block that we use here. Can you hear me, everyone? Is there a problem with my mic?
Just now have problem.
Oh, really?
Yeah.
Did you lose anywhere?
About the yellow line.
The yellow line? Oh, the
Yeah.
yellow line is the CPD, the critical path delay. So when we want, now it's okay, right?
Yeah, now it's okay.
Okay. When we want to find the total delay, we only care about this block, okay? This block, because we have to know what is the delay of this 4-bit adder, this block, and also plus 2 tau. And this 2 tau is coming from the mux, because if you could recall, mux can be expressed using an SOP, sum of product, which is 2 tau. Okay, 2 tau. So 2 tau is coming from the mux, and we add 2 tau with the delay of the 4-bit adder here. For example, if we are using the RCA, ripple carry adder, okay, the delay or 4-bit ripple carry adder is, remember, 10 tau, 10 tau. So you can check it again later. And let's say in the question it says here is carry loop ahead adder, like a simple carry loop ahead adder. So the delay for the carry loop ahead adder is 5 tau. Okay. So if this is the circuit, here is CLA and here is RCA, and then the delay is 5 tau plus 2 tau. So that is 7 tau, right? If this is RCA, for example, then you will calculate it as 10 tau plus 2 tau. That is 12 tau. Carry select adder, that's all. Not that hard to understand. Any question for the carry select adder? If you don't have any question, I would like to continue with the next type of adder, which is carry safe adder. So in among all adder that we're going to learn, so this is the last one actually. This is the most the fastest adder. Okay, in terms of delay, this is the fastest adder. So carry safe adder or CSA, what makes it different from the other two is it doesn't allow the carries to propagate. No propagation. But instead, it saves the carries in what we call as carry vector. What is the carry vector? Carry vector is this one. Right. And maybe you have realized this. Okay. Using the carry safe adder, we can add more than 2 inputs. Okay. As you can see here, we are adding value A, B, and C parallel together one time, right? That's why this adder as the speed, right? Well, in comparison, the CLA and the ripple carry adder, this type of adder will allow propagation. Will allow the propagation of carry. So this type of adder in general is called the carry propagate adder, the CPA. Okay. Now, let's see this example here. It is a 6-bit adder, 6-bit carry safe adder, and we are adding value A, value B, and value C. Okay, so 1, 1, 1 is 3, 3 is 1, 1, 1, right? 1, 1 is 3. So 1, the sum is here, but the carry is here. Okay, we save the carry inside the carry vector here. Okay, we're not going to ripple it up here. No, we're not going to do that. But instead, we save it in the carry vector. Right? Then next, 1, 0, 0 add up. So 1, 0, 1, 1 is 2. So the sum is 0. And then the carry is saved here. Right? Then next, 1, 0, 1, that is 2. So sum is 0, carry is 1. Carry is saved here. And 0, 1, 1, that's also 2. Sum is 0, carry is 1. And then 0, 0, 1 is 1. And then we use the carry propagation adder at the sum here and the bitwise sum here and the carry vector. This is not the total sum. This is only the sum at this bit location. So we call it bitwise sum. And this is the total sum. When we add the bitwise sum and the carry vector using the carry propagate adder, right? So we just add it normally. So this is 1, this is 2 here, because we propagate this time, right? We can propagate, means we can ripple. 1, 1, 1, 1, 1 here, and 1. Right? So that is how we implement it. That is the process of the carry safe adder.
So, Doctor, for the last step, we use CLA or RCA, right?
Yes, either one.
All right.
Depending on the design. Okay. So we have compressed the three stage of addition into 2 stage, because from A, B, and then B, C, A, B, and then you got a result, and then you add that results with a C. Instead of doing that, we add A, B, C all together in one step. Not like one step, but like in parallel. Okay, A, B, C together. Right. So since the C, you can design your carry safe adder using this part and this part. You can design it using any adder. Okay. Any adder. So, but this one we want to see the difference when using RC, ripple carry adder, and the carry safe adder. Okay. So the first one, here, the next one.
Doctor,
Video. Yes.
can you go back to the previous slide? Yeah, if we save the carry in the carry vector, it will give us different value or different result, isn't?
What do you mean different results?
I mean, if we add these two value A plus B plus C, we'll get different answers.
No.
I try.
Okay. Can you show it after the class to the group? Then we will discuss it. So you put it in a piece of paper, like you prove that the two calculation is different. Then I'll check from there. Can? Because I want to
Yeah.
speed the class. Speed up the class. All right. Okay. Now we're going to see how to add three number using only ripple carry adder. Because we want to compare this adding 3-bit number using a ripple carry adder only and using the CSA lettering. Okay. For this, we're going to see how to what is the difference is we are using the CSA. Right? So the ripple carry adder here, it's like A, B, C, and the sum. So basically, this is what we want to do. Okay. And it depends on how we design position of the adder, full adder and half adder. So up here is, if you are using the ripple carry adder, we can only add two. We can only add two input, which is input A and input B, right? So our ripple carry adder here. So our ripple carry adder. Okay. Not have the C will be added together later in the CPA. So this is the ripple carry adder. So this is how, not a good choice. This is how the carry propagate. The carry propagate. And this is how the sum of the first ripple carry adder from the input of the CPA, carry propagation adder. Or this is probably another ripple carry adder. This is another ripple carry adder. The ripple carry adder is a CPA, but this is the CPA part. This part. Okay, so the third input, which is C, is here. C0, C, and C3. And since this is also a ripple carry adder, so this is how the carry ripple, okay, the carry propagate. Right? And the last carry will become S5, the MSB. And the delay is 14 tau. Not going to elaborate on that, but it's probably because we have to this and this together, and this together, 2 tau. But that is not important. just remember that for this design, the delay is 14 tau. Okay, 14 tau. Or if
Sensei, we cannot hear you.
yes. Cannot.
Just now your voice was gone for a while.
Oh, okay. So it's just that you just have to remember that this pattern, the delay is 14. This pattern, the delay is 14. You can derive delay is 14 later. And then for the carry safe adder, we can add 3 bit into the adder. Using the carry input for the third input, which is the input C. And then instead of propagating the carry to the next, block of full adder, no, we're not gonna do that. Okay, the carry is going into the carry vector. And we add the carry with the sum, and we will get the answer. And for this one, just remember that the delay is 12 tau. Now is 9:21. Hope you can finish it. So the best carry is the carry safe adder here. So this is the delay. And this is number of bit length. Number of bit length. Okay. The longer number of bit in the adder, okay, the ripple carry adder will have more delay. Carry select adder and carry duplicate adder. The delay will also increase, but not as fast as the carry ripple adder. But the carry safe adder will maintain, even though we have a much longer bit length. Okay, that is all for the adder. Now is 9:22. I hope at least we can finish until the condition codes by today. Right? So now let's look at the subtractor. So for subtractor, I think you already have the hunch on how to do this. Like instead of having a sum and carry like an adder, we have the difference and the borrow, right? So 0, if we have input A and input B, 0 minus 0, that's 0. The difference is 0. 0 minus 1, the difference is minus 1. So we have to borrow 1. Get that? 1 minus 0 is 1. And 1 minus 1 is 0. So this is a 1 bit process. 1 bit process. Okay. So we call this a half subtracted, like 1 bit process of the adder. We call it half adder, right? So 1 bit process of the subtraction is a half subtractor. And the subtractor can be derived be like this because, like as you can see, the D here, okay, if you put it in a truth table, it will become an XOR truth table like A, B, E, right? 0, 0, 0, 1, 1, 0, 1, 1. That's 0, 1, 1, 0. This is the XOR characteristic. Okay. When the input is same, it will produce a 0. When input is different, it will produce 1. So that is XOR. So we can conclude that D is A XOR B. Okay. For the borrow, here are 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0. So it is 1 when A is 0 and B is 1. But it is 0 when both A and B is 0. It is also 0 when both A and B is when A is 1 and B is 0. It looks like if we complement A, 1, 1, 0, 0, 1, 0, 1. So only this will produce 1. That is an AND characteristic. AND characteristic. So we have R equal to A bar B. The half adder, the realization of the half adder will look like this. So when we want to continue the subtractor, this is half subtractor. I said half adder. So the difference with the half adder is we have an inverter here. Okay, invert the A. Right? And then for the full subtractor, the full subtractor here is we have the input A, B, and this is borrow in. Okay, so your full subtractor will have input A, input B, then we'll produce the difference, and there is another input which is called the borrow in or the RI and the borrow out or RI plus 1, right? So the input, there are 3, A, B, and RI. So the output here, D, is the results of 0 minus 0 minus 0, that is 0, 0 minus 0 minus 0, this is minus 1. Okay, this is also 0 minus 1. This is 0 minus subtract 1 and then subtract another 1. So this is minus 2. Right. 1 minus 0 minus 0. That is 1. 1 here. 1 minus 1. And 1 minus 0 minus 1. That is 0. 1 minus 1 minus 0. That is 0. And 1 minus 1 minus 1. That's minus 2. Alright? And from the truth table, you can derive the equation D and RI plus 1. Then This is the realization of the full subtractor. So we can use, okay, just like the half adder. Remember, sum in the adder is A XOR B XOR C, and the carry is AB plus AC plus BC, something like that. So it's same, okay, just with different notation, and of course there's a complement there. That's the complement, the half subtractor. So we can also make a realization of a full subtractor using a half subtractor hierarchically, okay, with the hierarchically design, which means we can also have a ripple subtractor. Maybe to calculate 0, 1, 0, 1 minus 0, 0, 1, 1, for example, right? We can use this 4-bit ripple subtractor. And then subtracting by adding. Okay. Now remember, A minus B is equal to A plus negative B, right? So how we get the negative B is using 2's complement, right? So the 2's complement, we actually have three ways to do 2's complement. Three ways to do 2's complement. Okay, let's say example, 4 bits. So B is 0101. Okay, one way to do the 2's complement is by invert all and then plus 1. So we invert is 1 0 1 0, and then we add 1. Okay, 1 0 1 1. Or we can just flip until we find the first one, right? Which is in this case, flip until you find the first one. So the first one is at the LSB. So we copy the first one and then flip the rest of the bits. So 1 1 0 1. And another one, flip, is we can use this formula, 2 to the power of n minus b, and this one. So this b is 4 bit, so 2 to the power of n is at the bit 5. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. So n is 4 because b is 4 bit. Okay, so we have 1 0 0 0 0 minus b. B is 0 1 0 1. Okay. So we want to calculate 0 minus 1. Cannot do that. We want to borrow from the next bit, but we cannot. Want to borrow from the next bit, cannot. Want to borrow from the next bit, cannot. Finally, we found 1 here, but we have to distribute 1 to all, but this one is right. So 2 minus 1, 1, then 1, 0, 1. So that is how you do the 2's complement. 3 ways to do the 2's complement, right? Okay. So that is how we can prove the S here. Okay. The results. We want to do subtraction, but only using adder. Okay. We want to do subtraction, but only using adder. Okay. The number that is subtracting, okay, is remain as it is, which is A. A want to be subtracted, right? A is remain A. Not gonna do anything with A. But B, because B is going to, we're going to subtract B from A. So what we do is we can flip B once, okay, flip B once, and then add with 1. Add with 1. So actually here we are calculating the 2's complement of B, okay, with 1 additional gate here to the adder, right? So that we can get the difference. So subtraction of A and B is A plus B or B prime plus 1. So we are doing subtraction, but we only use adder to subtract. So this is what the slide is about. We are using adder to subtract. Subtracting by adding. So just remember this formula. A minus B is equal to A plus B bar plus 1. Okay, now, time to wake up, everyone, because I'm going to ask you questions. Okay, now look at this circuit here carefully. Okay, I'm going to call names. Okay, Ahmad Iqbal. Okay, Ahmad Iqbal, tell me what happened. Now you left, eh? When I call names, you start left the meeting.
No, I mute my mic.
All right. Okay. If sub is 0, if sub is 0, what is the operation? So this circuit here is a 4-bit adder and subtractor. 4-bit adder and subtractor, and the multiplexer here will choose whether we want to do adding or subtracting. Okay. And the input that choose whether we want to do subtraction or adding is the sub. So if sub is 0, we are doing adding or subtracting. Ahmad Iqbal. Ahmad Iqbal? Ahmad Iqbal?
Yes, brother.
If sub is 0, we are doing adding or subtracting.
Adding.
Adding. Why? Why? Look at the multiplexer. Look at the multiplexer. If we give 0 selection, then what happened to B?
B perform subtraction.
B perform subtraction.
Or when sub 0,
When sub is 0,
it's perform as.
which B are we going to choose? Is complement or not complement?
Not complement.
Not complement. Okay, this one.
complemented.
Without the not complement. So what's coming into the FA is A plus B. When we choose sub is 0. Sub is the input that we can put. Is our input. Okay. Then if sub is 1, the multiplexer will choose the other way. The other way where the B is complement. The B is complement, right? And then, remember, A minus B is equal to A plus B bar or B prime plus 1. So, here in the full adder, we have A plus B bar when sub is 1. When sub is 1. And the sub is also connected to C0 here. The third input of the full adder. So here we have plus 1. So that is how we do the subtraction for this circuit. Right? Right, everyone? Hope that is clear.
Doctor, is the subtraction in 2's complement?
Subtraction is 2's complement? What do you mean? This B bar plus 1? Yes, it's 2 complement.
But the addition is going to be in binary, right? Or the same?
Yeah, it's in binary. The subtraction and addition, both in binary.
Okay, thank you.
A and B is just the value. So inside A you have A3, A2, A1, A0. It's just a definition. Okay. Right. So that is how we do the circuit that can do addition and subtraction. Right. 941. Let's go to the
Dexter, can you
condition
go back
codes.
to the... Hello, Dexter, can you go back to the circuit? So the first full adder, we feed subtract 1, but the second doesn't have 1. So how do we do the complement?
How we do the complement?
I mean, the first full adder, you add sub plus 1, right?
Yes.
A plus B bar plus 1. The second one, it will not have the plus 1.
Oh, it will ripple.
Because we're feeding... Yeah, but see, 1 could be 0 and 1, right?
Okay. I'm sorry. Okay. No wonder the one of you is confusing right now. It's this one. A0 plus B0 R plus 1. So this is only one bit and then it will ripple.
Yeah, but C1 must be 1 for us to do subtraction, right?
Oh, no. Not
Okay,
necessarily.
how do we get the plus 1 for it then?
So this is the subtraction of A and B.
Okay, how do we do subtraction A1 and B1?
Okay, listen. When you do this one complement, two's complement, okay? When you do two's complement of B is 1 0 1 0. Okay, you flip it once. 0 1 0 1, and then where do you add the 1? Where do you add the 1? Where do you add the 1? You only add it at the LSB.
Yes.
You only add it at the LSB. So only the LSB need to be plus 1.
Okay, if we add 1 plus 1, then we will have a carry, and that carry will go to the next bit, isn't it?
Carry is 0. Yeah. But this is B. This is... Where's everything? What do you mean, the carry?
like after we like this operation right now, you wrote 1 plus 1 is 2,
Mhm.
right? So you put 0 as a sum, carry you'll have 1, and that 1 will be added to the next bit, which will make the 0 1. But right now, if the first full adder is adding the first 2 bits, right? The
The
second
first full adder will
Yeah,
add bit A0 and B0, not the first 2 bit.
yeah, like A0 and B0. But then
Uh-huh.
right now, A1 and B1, how do we subtract? Just this
B1
one, I
and
just want to
B1.
know. Yeah, the next one.
Okay. We are subtracting by adding. A0 minus B0 is equal to A0 plus B0 bar.
No, this one
One.
I got. This one I got. Next one, like because
Next one.
yeah. So we have A1 and B1 on the next full adder, right?
Okay. A1 plus B1 bar plus
Okay.
C.
Yeah. So C, if C is 0, then it's not subtraction, right?
Yes, it's subtraction.
Even with Z0, we still subtract.
Yes, we only add 1 to the LSB. We only add 1 to the LSB.
Okay. Then okay, I got it.
Only this is the LSB. Only this one need to be added by 1.
Okay, yeah.
Right. Next one, let's see the condition codes. We have 15 minutes. Let's go this very fast, and because this is not that hard to understand. So the condition codes is codes. Okay, the codes that is placed somewhere in the memory. Special codes that is placed somewhere in the memory. So this is your memory. You have bit Z, bit N, C, and V, or we call it as flag. Okay, Z flag, N flag, C flag, and V flag. Z flag means a 0 flag, where the flag will be set. Okay, when we say the flag is set, means the flag the value of Z is 1 when we have an operation where the results, the bits, all bits in the results is 0. Right? And then we have N flag, which is the negative flag. So the negative flag is set when the sign bit is 1. Means the result is negative, less than 0. And then we have the carry bit or the carry flag. The carry flag will set to 1 if the most significant bit produce a carry 1. So we have calculation. Let's say we're supposed to calculate it to 8-bit number, but we have the carry out here 1. Okay. If the carry out is a 0, then the flag will not set. If the carry out is 1, the C flag will set. And then the overflow, when the result has too many bits to be represented correctly. Let's say you are doing multiplication, for example. So 8 by 8, 8 bit by 8 bit, you will get 16 bit. So to save it in an 8 bit, let's say this is 8. Okay, to save it in 8 bit, you cannot, because you have another bit after the MSB. So that will set the overflow flag to 1. Right? So the Z flag, okay, how to calculate the Z flag? This is only the formula. Okay, when all bits is 0, okay, then all 0, add all bits, and then you will get 0, and then you will complement 0, and then you got 1. So Z is 1 when all bits are 0. And this is for the negative flag. Okay, for the negative flag, we check the sign bit when sign bit is 1. Okay, when the sign bit is 1, like in our 2's complement, okay, then the results, okay, the number is actually less than 0 because it is a negative number. Okay. So the AND flag will set. And then the carry flag, we will see the carry bit. Okay, if we are adding 8 bit and 8 bit, the results, if there is an carry here, then the C flag will set 1. And then the V flag, so there are 2 methods to calculate the V flag, which is to use this 6 parameter, which is A n minus 1, B n minus 1, sum n minus 1, and C n minus 1. Sorry, this is sine n minus 1, and C n minus 1, and C n minus 2. 5 parameters. So let's say you are doing a calculation of 4 bit. So this is A3, B3, 3, A3, and C2. Okay? And the V will only set with this condition. Or you can check the carry at bit n and bit n minus 1. Like when you do calculation, check carry at this position and this position, XOR the two, and you will get the value V. Okay, so you can find the value V depending on what parameter info that you have. Okay. If you have these parameters, you can find it using this formula. If you have this parameter, if you know this parameter, you can use this formula. Okay. And then this is the realization of all formula for the Z flag, N flag, V flag, and the C flag. Here, from this circuit, we have S0, S1, S2, S3. When we this is not X no. When we put all the sum value to the sum bit to the norm gates, we will get Z, okay, the value of Z. And by looking at the MSB or the S3, we will get N. And by XORing C3 and C4, we'll get V. And the C is directly from C4 carry bit. Right. So this circuit, again, if sub is 0 and if sub is 0, we will do adder or subtractor. Adder or sub. Okay. That is for you to see before we end our class. So to define whether it is sub or add, so we must make sure C0 here is 1 to get its subtraction, right? So we can draw the truth table of sub and C in 0, 0, 1, 2. This is XOR, so 0, 1, 1, 0. If the sub is a 0 and the C-in is a 0, then we will do addition. If the sub but B here is also using XOR. So check B and sub 0, 0, 1, 0, 1, 0, 0. So which condition? Which condition will be subtraction? Okay, I will ask you again this question before we start the class next week, Sunday. And this is the last slide for today. We have less than 5 minutes. So why we are learning about this condition is because like when you want to write a program, you always use this condition, right? If A equal to B, for example, if A not equal to B, okay? If A less than B, A less or equal to B. So you are using this condition in the program, okay? When the computer compile your program, so inside the hardware, what it was doing is they are subtracting A minus B. Okay. If this is equal to 0, means this is true. If this is not equal to 0, means this is false. Okay. So when we want to check if this is equal to 0. How we want to check? So when the results of A minus B is 0, okay, the Z flag will set to 1. So the computer, the hardware will only check one bit here. Okay? Bit Z. The computer will only have to check one bit instead of checking every bit. Okay, is this bit 0? Is this bit 0? Is this bit 0? Okay. If you are doing 32-bit calculation, that will be very long checking. You have to check 32-bit to check all bits are 0. But instead, we only check the Z flag. Okay. If Z flag is 0, then we know that this is false. False, because it's not set. Okay. Z is 1 when the answer of A minus B is all 0. So if Z is 1, then we know that this condition is true. Okay? And same goes to the rest. Okay? So if we are checking less than, then we can check the carry or the N flag and the V flag. If you want to check the less or equal, we can check the carry and the Z flag, okay, and so on. Right? This is XNOR for those who don't know. Right. So that is all my class today. For next class, we're going to start with from this slide, and then we'll finish multiplier, and then we will go to the case study of the combinational circuit. Right? So that's all for today. If you still have confusing questioning regarding these circuits, or the one that Anas picked up just now, he said the calculation is not the same. So let's discuss in the WhatsApp group. Okay. So that's all for today. I know you probably have class.
Doctor, I was wrong. Yeah, the answer is the same.
The answer is the same. Okay, thank you. I hope you can focus. The rest of the class, not calculating that only.
Okay. Yeah, I do.
Yeah. Okay. Thanks. Okay. So that's all for today. So see, that's a lot that we learned today. Hope you can still be awake after this. If you still have class after this, okay. Good luck for the next class, and see you next week, same time, 8:15 on Sunday.
Doctor,
Yes.
is there any difference between the blue CBD and the red one?
Blue and the red.
The blue CBLD and the red CBLD, because I have
no different. There's no difference.
Because I tried too many times to program it, but I still cannot.
You see, the CPLD is the chip. The blue and the red is the board, where you put the CPLD chip on the board. So the difference could be only the board. The board is different.
Because my friend has burned his CPLD today.
Your friend has what? Sorry?
Burned his CPLD.
Oh, burn. Burn is